Hi everyone, welcome to this supplementary video, this short supplementary video where I discuss the pressure boundary conditions, pressure jump boundary conditions as you have seen in your homework. Pressure jump boundary conditions. And essentially what I want to get right here is how to use the signs in this equation, how to use the correct, or how to be consistent about your definition of the normal vector and understanding physically what it means and also the signs of the curvature that you will find when you make this definition. So essentially we're looking at problems where we have a surface. We can have something like this. Maybe a two-dimensional surface. Let me try to draw it again. So we have a two-dimensional surface with a vector n. And on this side here, we can have the stress vector S of n that acts on the surface. And here I'm gonna call my surface S. So according to my definition of the normal vector, this would be side 1 and this would be side 2, or phase 1 and phase 2. It points into the phase with the higher number. And the surface tension would act along the contour, so for instance here, and it's pulling in this direction. So it's pulling like this. That's what the surface tension would be doing. The book goes into a little bit more detail about how to find the boundary conditions, which we don't derive here. We just state the boundary conditions, which essentially in the normal direction, they give you the jump in the pressure if you have surface tension, if you account for surface tension. And the original form of that would be pressure on side 1 minus pressure on side 2 minus the divergence of the normal vector times the surface tension equals 0. And so a point that I want to make clear here is that there is some arbitrarity in the definition of the mean curvature. The book defines, and we follow the book in the definition, h equals minus the divergence of the normal vector over 2. And that's why we find the equation in the form that we're probably more familiar with, which is pressure 1 minus pressure 2 plus 2 times the mean curvature times the surface tension equals 0. So that's the form that we're used to seeing. And so the point that I want to emphasize here is that this definition of the mean curvature is typically people define it as some constant of the divergence of the normal vector, and it can be positive, like plus the divergence, or it could be, in the case of the book, minus the divergence and over 2. So what we're going to learn in this supplementary video is how to be consistent about the choice of the normal vector and how to interpret the result physically. So the example that we're going to use to that end is the example that you solved on your homework. Example in the homework 3, and it's problem number 3, where we had a plate and a fluid like this. Here below the surface, we have the fluid phase, the liquid phase, I mean. So this would be the liquid phase. So gravity would point downwards like this. This would be liquid, and this would be my air phase. And the surface is described by an equation of the form z equals h of x. So the height of the surface is defined like this. I can say here I have a coordinate system. This is x, and this is z. So the first thing I want to point out here, and I hope to be quick, is that either choice of the normal vector will give you a consistent equation. So choice of the normal vector n hat gives you a consistent boundary condition. And I can prove that making both of the choices for the normal vector. We can start with the one that we have had for the latest version of the homework. which is then pointing into the air phase. And for this choice, N pointing into air phase. Our definition of the phases would be N pointing into phase 2. So phase 1 would be the liquid, and phase 2 would be air. And the equation for the pressure jump is always the same, this pressure boundary condition. It is P1 minus P2 minus the divergence of the normal vector times the surface tension equals 0, which is the first equation that we wrote. What I want to show you is that if you choose the opposite direction for your normal vector, so if you choose it to point like this, and you say this is a different vector, n star, then your definitions of your phases will change as well in accordance. So we would have now pointing to phase 2 star. So that's my phase 2 star. That would be the liquid. And my phase 1 star would be air. So I would have the vector n hat star pointing in the opposite direction. So that's minus the normal vector that we had previously. That's pointing into the liquid now. And we have phase 1 star is there. Phase 2 star, which is where it's pointing now, is the liquid. You will find, following the same convention, the equation P1 star minus P2 star minus the divergence of my normal vector, which is now n star, n hat star, times the surface tension equals 0. Now, if we take the equation that we found using this convention and reintroduce the definitions from the previous case, where we defined the vector normal to be the opposite, we would find that this is a consistent equation. Or in words, but this is the same equation found previously. Because the definitions that we made relate to the previous definitions as follows. Pressure 1 star is what I previously called P2. Pressure 2 star is what I previously called P1. And the divergence of my vector, normal vector n star, is the divergence of minus the normal vector because it's pointing in the opposite way, so it's minus the divergence of n. And that gives me, from the equation that I found, P1 star is P2, so I would just write these P2 instead. P2 star is P1, I'll write minus, I'm gonna write minus P1 then. And we flip the sign for the divergence. Since now divergence of n star is minus the divergence of n, we get plus the divergence of n here times gamma equals 0. Or if we invert the signs again to be to write it in the same form as the previous equation, we will have P1 minus P2 minus the divergence of n gamma equals 0. So this is the same equation that we found previously, and hence it does not matter whether we choose n to point into the liquid phase or into the air phase, we will get a consistent boundary condition. Now, the second thing that I want to talk about, and this is also an important thing, is how to use this equation to get the correct sign for the term associated with the curvature. So getting the correct sign in the BC and understanding it physically, which is, I think, the most important bit. Physically. I should rewrite this. I should rewrite this again because I misspelled it. What it means physically. So let's go to another page and let's go through the calculation in the example that we had for the homework. So the way to do it is straightforward. You just follow the definition that you used, the convention that you used for the normal vector. Essentially, just be consistent. With the definition of the normal vector you chose. I'm going to call it n hat. For instance, I'm going to draw the schematic that we had again. So we had a plate, and then we had a surface and the fluid below the surface. And this is the convention that I followed here. I chose my normal vector to point into the air phase. If I want to achieve that, I can write my surface equation as this. Z minus h of x, which equals 0, because z equals h of x. And so since the surface corresponds to a constant value, in this case 0, of my function of x and z, the gradient of f will point normal to the constant values of the capital F function. So I can write it as the gradient of f, but I also need to normalize it. So I need to write it like this. And the gradient of my function is the derivative in x times zx plus the derivative in z times ez, because it doesn't have any y dependence. So it's just partial derivatives in x times the basis vectors, and your x and z times the basis vectors summed. What I get out of the expression for the function is, if I take a derivative in x, it's going to be minus h prime. So minus h prime times ex. I'm writing the derivative as a prime. And here, if I take the derivative of z, it's going to be 1. So it's plus ez. Now, if I want to calculate the magnitude of this vector, I need to square the components, sum them, and then take the square root. So df dx squared plus df ez squared, and then I take the square root. We already calculated the components for the gradient. So this is the first component is minus h prime. When I square, the sign won't matter, so it's going to be h prime squared. And when I square ez, I'm going to get 1, so I'm going to write it in the opposite order. I write it like 1 plus h prime squared to the 1/2. But I want to know the divergence of n, which is what goes into the pressure boundary condition. So I take the divergence of the normal vector, which is the sum of the partial derivatives. And the sum of the partial derivatives is going to be, or let me first write the normal vector itself. The normal vector is the gradient of f over the magnitude of the gradient of f. So it's going to be minus h prime times ex plus ez over the magnitude 1 plus h prime squared to the 1/2. And now the divergence of the normal vector is going to be the sum of the partial derivatives with respect to x and respect to z. So that's going to be the derivative of respect to x of minus h prime 1 plus h prime squared to the 1/2 That's the first term, and the second term should be a derivative with respect to z of the same of the second component, and the second component would be 1 plus h prime to the 1/2. We see that there's no z dependence, so this term goes away. When I take a derivative, it's 0. And for the other term, we can do the math. It turns out to be minus h2 primes over 1 plus h prime squared to the 3/2. This is the sign that you would find, and that's why the sign is associated with the direction that you choose for the normal vector. So just taking the derivative of the normal vector you find can give you the minus sign if it points into the air, or the plus sign if it points into the fluid. You just need to use it consistently into the boundary condition. So that's what we're going to do now. So in the pressure BC, we are going to have, just writing the boundary condition again, divergence of n times gamma equals 0, or minus B2 equals divergence of n times gamma. And it's important to notice now that the divergence of n, which we just calculated, the sign of that term is determined by h2 primes, because the denominator is positive. It's the square root of a positive number, cubed. But we have h2 primes determining the sign of the divergence of the normal vector, which goes into the pressure equation that we just wrote. So if we want to know which pressure is higher, P1 or P2, we should look at the divergence of the normal vector. What that tells us is we have a concave up curve in this case. So h2 primes is positive. And since h2 primes is positive, the divergence of the normal vector is negative, because it has the opposite sign. It's minus h2 primes over something positive. If h2 primes is positive, then the divergence of the normal vector is negative. So we have this pressure condition for the this pressure condition where the divergence of n is negative and the surface tension is positive. So that gives us something less than 0, or E2 is greater than P1. Physically, what does that mean? And that's the point of this supplementary video. So physically, if we look at the surface here, and the liquid is on this side, we can zoom in on part of the surface, which is highlighted here. So we zoom in on the surface and we have something like this. Surface tension acting on one side, surface tension also acting on the other side. The pressure is compressing on the side of the liquid, which is side 1 according to my definition, like this. And it's also compressing on the other side, like this, E2. But we notice that, I'm even going to draw this again, like this. We notice that the net effect of the surface tension is a force in the same direction as P1. So surface tension exerts a net force in this direction, in the direction of P1. Force in the same direction as P1. And in order to maintain equilibrium, we have the contributions of both P1 and the surface tension in the direction of P1. And so P2 has to be higher than P1 to account for that difference due to the surface tension. We would have P2 has to be higher than P1 to maintain equilibrium. So that's the physical interpretation. We have P1 and gamma acting both in the same direction. P2 has to be higher to compensate for that. And that's a more general statement that we can make. We will always have one convex side and a concave side. So the convex side, which could be connected by lines, points inside the convex side could be connected by lines within the region. Well, the full line is within the region. We can't do that to all points of the concave side. But the point is that this is just an example for this general surface, two-dimensional, one-dimensional surface. But in general, we will have a convex side and a concave side. And the conclusion holds for the general setup too. So we have a convex side and a concave side. Locally. Also because that can change we can have a surface which changes curvature or the sign of curvature along the spatial direction. So we could have something like that. Like say we could have a sinusoidal surface and then it's concave on one side and then that the same side, say the liquid phase or the air phase, you can be concave and then convex if you look at different points within the surface. But what I'm saying is that we can have a convex side and a concave side locally. And pressure will be higher on the convex side. And the reasoning is the same. If you look at the drawing that I just, the schematic that I just made, we have a convex side, which is balancing both the pressure on the concave side and the effect of surface tension. To balance both of these, it has to have a higher pressure. So that's the physical interpretation behind the pressure PC, and I hope this helps. So see you in the next supplementary videos in the lecture on Monday.